as I told you, that omega is the quantities that we are interested in, extensive properties, and it can be shown from general considerations that omega goes as an exponential n, say a to the power n, and then free energy or entropy, they become proportional to this. Alright. So that is the one. So you want to maximize the entropy. You can easily do that by taking a distribution and try to find out the distribution. And then go from that distribution. Actually, you have done that in your entropy of a binary mixture calculation. You have done that. So that becomes RT, right? N comes out of the calculations we do it. And that is always preserved. It is a very important thing in a theory to guarantee the extensivity of the thermodynamic properties. In quantum, they suffer a lot to do that at the higher level of the theory. In statistical mechanics, because of this combinatorial factor and several other factors, which is, I don't think the theory was built in to explicitly account for the extensivity. The theory was done well, developed correctly, and so the extensivity, followed. So it is ln omega that is the primary quantity. That's the first thing to remember. Second thing to remember, that you have to maximize the omega. Third thing, maximize ln omega. Third thing to remember, that I cannot have any distribution because there are these two conditions. Fourth thing to remember, so you can make a flow chart. That how do I find the extremum of a distribution, not function, but a distribution. You have done all well from your high school days, how to find the maximum and minimum of a function, right? Here you are not doing it for a function, but rather you are doing that of a distribution. And the distribution is Nj. And then you get, you use the Lagrangian multiplier. If you are not interested in the details of the formula, then it is trivial. The method of undetermined coefficients, you have to just look at the equation and say, okay, I have D and J, or D and K if you want to separate K from J, you have a specific equation. Then you have the ln omega, then you have minus alpha, and that condition, and if you inspect the equation, that is already, that itself satisfies the maximum condition. You are not changing anything, but it put the constraint. Do that, the derivation has been given to you. It's not a difficult derivation, but it's a, these are the things which should be done in undergraduate BSc. Like there is a book called Art of Mathematical Physics. That is done. Mathematics should be done at a high level, because if mathematics is not done at a high level, what will happen? You probably don't realize, without you realizing, that many branches get close to you. You don't have to. You don't realize. Students don't realize that at all, because they make the choice on things what they can do, and that essentially. Now, so when you do that Lagrangian multiplier, then we get a condition of Nj, and that Nj has e to the power alpha, e to the power beta j on the other side, and then you bring it on the e to the power of u to the summation, and okay, this is what I was saying. So that Nj star by n, it gives you the probability distribution. That what is the occupation, and I told you it is not n, it is nt, the total number of systems in our supersystem. So Nj is the number of systems. Very interesting. It is the number of systems which are in the energy J. You have seen this form many times where your system is just a spin or system is a particle, and you are distributing that, like you have done in Boltzmann distribution. What is the probability of being in energy level J? There, that particle or that particular molecule or electron is your system. So it's a very general definition. So I have this capital NT number of systems in my super system, and as I told you repeatedly that we construct all this framework, and this is very mathematical and very beautiful, but mathematical and not easy. And both quantum and StatMech are very mathematical, but mathematics that is involved at the early level of StatMech is tougher than what is involved in early level of quantum. But later time, quantum math also becomes extremely difficult. Now, so we have that. What happened to that? There is some pointer I needed. Can one of you go and bring a pointer? So now, then this is a very important equation. This particular one is that we are taking here. This equation is a very important one. And then that is a beautiful structure. I can sum over Nj, and Nj is the number of systems in energy level J. So that becomes Nt, that becomes 1 inside. Then I can bring it on the other side, e to the power 8 alpha this. Then I put it back. And then this comes in the denominator. And then we get this equation that is on the board, because Nj by Nt, and we put a star. This star is put to say that it is done by most probable distribution. Now, there are several important comments which are in order, and that is an important. You should have asked the question now: why you are doing with most probable distribution? What tells me that the most probable distribution is the valid representation of the system? And the reason I gave you the answer directly, and there is a method in mathematics called maximum term method, which shows that when you get, so one thing to realize that Nj is a distribution, is a set of numbers. It is not one number. It is the distribution itself. That distribution we have maximized, and we say, okay, this is my distribution. Now you can ask me why it is correct, why you did by most probable method. So I'll give you the answer straightforward, and I'm not going to derive it because it will take us pretty deep into many things in StatMech, but it is given in some books, like it is called maximum term method. This method that we are doing called maximum term method, and there is one of the stalwart of statistical mechanics called Joseph Mayer, and we'll do one of his theory if time permits at the end. Now, here's a book, Statistical Mechanics, Mayer and Mayer. Maria Goeppert Mayer and Joseph Mayer. Maria Goeppert Mayer was the wife of Joseph Mayer. There are a lot of stories about them. And wife got the Nobel Prize, but the husband did not. The husband did a lot of very nice work. Now, they wrote their book on Statistical Mechanics. And in that book, you can find a lot more on the. These two books are very important, those who are interested. And I think you just take a look, because it's a beautiful subject. Seldom you come across such a subject in your undergraduate. One is Tolman, Statistical Mechanics. There is, of course, a beautiful book by Feynman, but that's very quantum. Again, Statistical Mechanics. There is a book by Hill. But the one I'm saying today is Mayer and Mayer. They are all in library. IISc is very good in old books. In the Mayer and Mayer, they have the maximum term method. So, So let me write down. So what you can do now, that if you can do, how come it will be working? It didn't work yesterday, Tuesday. Oh, then we'll keep this. An SSC office. Good. Okay. So, what you can do, that you have done this distribution. So the distribution you find is exponential is energy. And now you can calculate it exactly. And what you can show that when you calculate the distribution exactly by an average, then you can show that as the system n going to infinity and v going to infinity in this limit, that is shown in the difference goes to 0. Or the distribution that you get by doing exactly, and the difference between that, or rather the second moment of the distribution and the exact distribution of the second moment, when you take the system, this we call thermodynamic limit in statistical mechanics. Very important limit that will make the size of the system go to infinity, total volume going to infinity, and the difference between the exact calculation and the maximum term method that just disappears. So that's why there is a lot of study on this so-called thermodynamic limit that is that. Okay. So the main point is that this we are talking about distribution, and the distribution is right now is what we get is the Boltzmann distribution, which you have known from your language. So now there is an alternative derivation given by several people, which I have given here, which is many people think it is simpler, and that appeals to you divide the system and the path, and then you can consider variation in the energy by doing a Taylor expansion, and then you can use the thing that we already know in microcanonical ensemble. This quantity we have done in microcanonical ensemble is 1 over T. Okay, that was only the result. You use that and you can get the same result of the distribution. So I'm not going to do this because I have already done one derivation. I don't think we have the luxury of doing 2-3 derivations. But this is a derivation, you can look at it, it's in the book. Okay. Now, the important part comes. See, in microcanonical ensemble, what did we do? We got a distribution, and then from omega, and then from there we showed how omega is related to thermodynamics. So one of the basic premise of statistical mechanics is that we want to connect it to thermodynamics. So you would like to know, okay, this is my partition function Q, that is here, which is sum over d to the power beta j. Now I have done all this work to find the distribution of energy, and I have an expression for this partition function. But what good is this? What can I do with that? How do I use this? This is an extremely important thing, because about 4 lectures from now we will be doing the exact calculation of this quantity. That means we will be evaluating partition function, and we will be evaluating the thermodynamic properties. But let me show you today how to do that. So just what we did in microcanonical ensemble, we define an average energy, and the average energy is just EJ/PJ, right, or PJ/EJ, and then it is this quantity. Then you could actually guess how it will go from our microcanonical ensemble. There also what we did, we took a derivative of the omega, right? And then you express the omega, the differential of omega, the total number of states in the system, which I call the partition function in the microcanonical ensemble. And that we now expand these variables. What are the variables in micromechanicals? NVE. And then we go to Euler equation. And then we write the omega is ln omega is s. So I have a ds for microcanonical ensemble in terms of omega. Then I write the identical equation for Euler equation from Euler equation. And then we do certain cyclic rule and other things. And then I get back, which is given Toto in book. And I think, Shui told me that there has been some complaint about not giving the details. Partly true, because we had to remove some equations, because at the end of the day I didn't want a book which has too many equations. You can have books like Tolman, which is a wonderful book and I like, or Feynman, where equations are given but intermediate steps are hardly given. Famous is Landau-Lipschitz. That's the best book in StatMech in the world actually, but very difficult book. That's the best book. If you can read just the first paragraph of that, the first chapter, Landau-Lipschitz. See, purpose of a course is take the students to the door and open the door so that you can, students can enter through. The purpose of the course is not to spoon feed you. That's a mistake we do in schools and colleges. That's why you don't get good scientists at the end of the day. Okay. Now, so I usually, this derivation student have to do the intermediate steps. It is not so difficult. If you expect that everything will be given for you, then you won't be able to read Feynman at all. You won't be able to read Landau-Lipschitz. Landau-Lipschitz is notoriously not giving intermediate steps. There's a little bit more in my book, but others is that in the beginning I didn't know, I gave it 575 page to the publisher, and publishers once they said anything less than, it becomes more than 700 pages. So we had to cut down, so remove some equations also. That's the inside story, except I never like too many equations anyway, because that one can do. One should not destroy the flow of the book. Okay, so this is the average energy. So now I take the differential, exactly what I did before. Okay, that I take the average E of that and then I put that. Then you can understand and then tell me what will be the next step. We can sit for the whole day. I don't care. What is the next step? We have Pj here. That's the starting equation, right? Alright. Then I have dPj here, and I have a very interesting combination. I have the combination of, if I take dEj here, think a little bit. If I do dPj here, what do I get? I get 1 dEj will come out. Okay? And 1 will come also from the denominator. The one that will come from denominator is a minus sign and 2 minus sign will give me an average E also. Okay, so you can start seeing the pattern that I am going to do. So I do dE, I put that exactly what I told you, ln Q will come out. And ln Pj from that equation, and then I expand my dEj. So with the dPj I play that game. Okay. And for dEj I expand it in dV. Okay. Now there is a very interesting thing that you can use when you are playing with that conservation of probability is Pj equal to 1. So sum over dPj, which is here, will go to 0. Do this. This is a lot of fun doing this math actually. Okay. And if you don't get everything done here, but you will see that if you just have to take the way to do, go and just take the dP. Just take the dP here. Everything will follow. And remember, this is Q. Okay. All right. Then we also know, we already use S equal to minus KV Pj ln Pj. Now look here now, this term has disappeared. I have ln Pj here and I have dEg dV here. Now let me start with this quantity, Pj ln Pj. So, I now write, put the ln Pj term here, and I have to take a d. This should have been a little better done here. Okay, d here. So I have to take the differential. So this term I am going to use now, and we are taking the derivative. So we will now take the derivative here. What do I get? I get one term. This has been done very explicitly. Should not have been done that explicitly. It becomes 1 over Pj dPj, d of ln Pj. Okay, and this then become, and rest is ln Pj dPj, because I take the differential of this and I take differential of that. Okay, so ln Pj becomes 1 over Pj, and that is here, and that is that. Suddenly I have done great gusto to all the details. Now we can combine these two equations to get dPj equal to dE plus Pdv. Okay. Why? Because we already have this equation here. So this quantity then, dEj dV is becomes, so let us do that a little bit more now. So dou Pdv, I am getting Pj, and then that becomes Pj by Pj becomes 1. So this dPj term again goes to 0. So I have ln Pj dPj. So I goes to this equation and get from there ln Pj dPj. So that left hand side comes on the this term comes on the right hand side. Okay. So we have left with ln Pj. Again go back. ln Pj is this term is going to 0. I have ln Pj dPj left. Here also I have ln Pj dPj left. Ln Pj dPj left. Here. Here. So I now solve for ln Pj dPj. This term is not there from these two. And I get then this quantity. I am making that derivative of energy with respect to volume is the pressure. That is one thing that has been put in here, and that I can do other way. Now I compare with the, so this is my kVt ds, this ds. So I combine that with this equation that I know exactly. Okay, so if I combine with this equation, then I get, so this is the condition then of the entropy. So this is the entropy and this I know. Then that allows me, this comparison allows me to tell this beta. So there is TDS here, the beta is 1 over kVt. So then I go back and I get S, which I know E by, now go back there. Is a little bit circuitous. So okay, I see that. Anybody sees how it went? This equation 5.38. You guys don't take note anymore. Huh? If you take the reward, then look at this equation and tell me how it is coming. Okay, can you come to the board and read? clean before, clean before. Same thing right on the right hand side. Wait, I told you one more. Good. Thank you. So what has been done? Now, now we have to figure out that this equation. So that uses the definition of. So we now go back to this equation. Right. So now we have ln q dpj. We just showed ln pj dpj is the ds, right? So this term and this term is ds. This term and this term, without that is the ds. Okay. Now we have this is quantity, which is the pressure. That also you get by comparison. When you put that into this equation, then you get S equal to E by T plus A. Okay, that means you are getting from differential to the A form, the integrated form. And if that is the case, then we already know that the condition of homogeneity is A equal to U minus Ts. So that condition is used here. The important. So I think one should have written one more, few more lines here, which should have been explicitly doing here the help. If that is so, then free energy is minus kVT energy. So this relation comes out. Okay. So S. So you write kV ln Q, kVT ln Q. So Ts equal to E kVT ln Q minus A, and we know A is the minus Ts. You write here A equal to E minus Ts. So that now gives you to compare these two quantities, E by T and E by T. You compare these two quantities, and you then get minus A by T equal to kV ln Q, and then A equal to minus A. Is that okay? If you have any confusion, tell me. We can go through that because these are important information. As I am telling you, it is the most fundamental and most useful equation of statistical mechanics. So we go back, do it once more. We start with this equation dE, then we make it E, and then we make it dE, and then we write, go back to the derivation.
definition of Pj, and I do Pj I expand and Pj dVj, and then this quantity is the pressure and the energy J, and I sum over Pj, I sum over this Pj by this Pj and get a capital pressure, capital P, which is the pressure, or small p, whatever, but the energy level, pressure at energy level J is small pj, that's the pressure, and you multiply the probability of that. When you sum that, you get the pressure. Okay, that to keep in mind. And now use this condition, conservation condition, then we bring in the entropy which we used in microcanonical ensemble, and then we take a derivative of that, ds, just like we did before in microcanonical. We get this quantity, and then this goes out. I am left with the important relation is ln pj dpj and ds. Okay, and then one compares that with this condition which you already know, TdS equal to dE plus PdV, and then as after did it here, or that you get this, from this you get this relation, which is actually fairly trivial once you go to the steps, but it will circuitous, that is, you can get trapped. When that is done, then you get, so S is so okay, S is Pj ln Pj. Now you have to use Pj ln Pj here, where you go back and you do the Pj ln Pj here. Ln Pj brings out Pj and minus ln Q. Now if I now multiply it by ln Pj, I multiply it by Pj and sum over that, then Pj ln Pj give me E here, okay, and ln Q sits out, sum over Pj just give me 1, okay. So then I go back and I get so this is the condition then. This is the S equal to sum over Pj ln Pj. I go back definition of Pj, put the ln Pj, and get by this derivation sits out of the derivation what we did before. You know, it is nothing to do with the beta equal to kβ. So there are two things that have been done side by side. This would have been done earlier, then one should have shown beta equal to kβ because this is more important and it is more trivial. Derivation is the trivial. So you invoke this one, then use the definition of Pj which derived, and you get this condition because I take ln Pj bring out Ej, Pj outside, Pj Ej is the average, okay, and I have ln Q coming out and sum over Pj ln Q, Pj is 1, so I just get ln Q. So S equal to E by T Kp ln Q. This uses just the definition of Pj in terms of partition function Q and Boltzmann distribution. Nothing else it requires to derive. So I combine S equal to minus Kb Pj ln Pj with my definition of Pj and I get this. Then I compare, so I derive this one, this beautiful equation, E average by T, KVL and Q. And now I know that A is equal to U by T minus 8. Then I compare this equation with this equation, and A equal to minus KVL. So this derivation is trivial. Everybody got it? So why we need the earlier equation before that? Actually, we don't need that.
So we need it because we have to put the value of beta.
We have to put the value of beta in this place, right?
Yeah, when
We are at this place when I keep the ln,
yeah.
beta comes out. So I have to put beta equal to 1 over kVt. Otherwise, I won't get this 1 over temperature. Okay. So this is the as I told you, most important equation of the entire statistical mechanics in terms of the partition function. QNVT, and the derivation is a little bit circuitous at this level. Going through DPJ and going this repeatedly, you repeatedly use that, and you have to bring in these equations and combine with PG and kind of a messaging the whole thing to get that out. Okay. So now, as I told you, why this is the most important equation of thermodynamics, statistical thermodynamics. First time, this is the one that your Q is just a sum over e to the power minus beta. So if you have the energy levels, you have the partition function. So if you have the energy levels and have the partition function, then you can get this. So what this statistical mechanics tells you, that you have an exact expression from the energy level. So if I do get the energy level somehow, either quantum mechanics calculation, but some other methods, but in classical statistical mechanics, you don't need to do quantum problem, but like in interacting gases or ideal gas, then I can calculate. I'll show you very, very easily the partition functions, and you get all the results which you know already. But so this is there are many reasons why this equation stands out. Now we'll show why. So one of the same thing we did this is the standard thermodynamic, sometimes called the fundamental relation of statistical mechanics. Now, you now get all these things we know. Now, entropy is obtained by the derivative of the energy. So I can now write the entropy of the system in terms of this one. A equal to minus KVT ln Q, so d dt. Get this first term comes out because of the temperature, and minus makes this positive, and this is KVT ln Q. Okay. This pressure, then I know pressure equal to minus d dt. So now I get the pressure in terms of just the derivative of the partition function. So both entropy and pressure is obtained from the derivative of the partition function. It is very important because you don't have to do an integration. Doing integration brings in a lot of complexity because of the limits, and in addition to that, you have to do the integration. Doing differentiation is easier of a function. So these are the important things that comes in. Then one goes to grand canonical partition function, and the grand canonical partition function is again a fairly complicated thing. But without going into that, let me tell you a little bit more of the partition function. So the quantum partition function is sum over the energy levels. What would be the classical partition function? Actually, classical partition function was written down before the quantum partition function, and we'll be using a lot more of the classical partition function. So classical partition function. So what could be the expression of the classical partition function? let us consider a system of gas particles or kinetic theory of gases, a number of particles in a volume V and temperature T. Now I know that I am going from quantum to classical, though that was not the way it was done. What is the classical counterpart? Classical counterpart, you have to now think of where the EJ comes from. EJ comes from the Hamiltonian, right? Now, in quantum mechanics, when you integrate over, in quantum mechanics, you do not have the position and momentum because of the uncertain principle. But in classical mechanics, you have the position and momentum well defined. So one can make a transformation. There is a beautiful method of doing a transformation from energy levels to momentum and a space, and that is called Wigner transformation, which I am not going to do. But I can now write down, but you will be able to realize as soon as I write that down, all the coordinates of the particle we are in, all the momentum, this is the quantum, the classical partition function, Qn dV 1 over n. Why the n factorial put in? Distribution, right? So this is the classical. There is one more thing missing, and that it took very long time to get it. These factors sometimes got much better. But there is one thing is this. Now, if I now put a psi here and a psi there, and then that psi j and psi j, they are sum over j there, and then this beta h will act on psi j, will give you e to the power minus ej, and then this will, you can reduce this expression to exactly this expression. So these are, this is a quantum and this is a classical partition function. They are, you can evaluate both of them. It's a lot of fun to evaluate them. For example, particle in a box, and particle in a box, where you know the energy levels, n square is square by 8 square, or harmonic oscillator, you can calculate the quantum partition function, and then you can see that by going to large temperature limit, you go to zero limit, you get back exactly the same partition function again. Okay. So I think we'll in 5 minutes we'll stop. So this is the quantum part, and there's one thing is missing. Just I want to draw your attention that what is the dimension of this partition function? This dimension is. What is the dimension of this quantity? What is the dimension of this quantity? Okay, forget about n. We will put n. So this one is the length and this is the momentum. You guys know the form. Say, who said h? So what was missing when this was done by first Boltzmann put it in N factorial, but this was not done, so people happily was working with that because it needed. But later, when you evaluate the classical partition function, for example, particle in a box or how many percent, and you calculate quantum and the classical and you compare them, then you find the thing that was missing in earlier discussions were 1 over h to the power 3. Okay, and h is the Planck's constant. Planck's constant is the energy multiplied by time, right? In arc second. That is the energy that time is constant. Okay, so now forget about this. So this is very, very important no, because it becomes a Dubovny wavelength and all these things, and goes over to quantum mechanics. And Dubovny wavelength enters into it in a very prominent way. Now, tell me, if I have a particle system like that, a bunch of particles. Now, let me see the particles are not interacting with each other. They are ideal. So the terminology of ideal gas, noble gas, actually noble gas is not ideal in a true sense because they do collision with each other. But ideal gas, the particles of phantom particles, they don't interact with each other. If they don't interact with each other at all, then what becomes your Hamiltonian? Tell me what becomes your Hamiltonian? Just kinetic energy. Correct. And then kinetic energy means just Vj square by 2m. See, all the particles have the same mass. Okay. So now I put it sum over Vj square 2m, right? Now, how do I integrate this quantity? So these are ideal gas of particles who don't interact with each other at all. They don't know that other particle exists. Then what happens to this integral? So I can integrate these things to a volume. Okay. So then I get 1 over n factorial L to the power 3n or V to the power n. Each particle explores the full volume. Okay. Now what do? I do the integration. So integration dp1 vector dp2 vector dpn vector e to the power minus beta. Remember the beta in the prominent way everywhere, whether classical quantum mechanics, beta has to be there. This plays physically the important role because temperature determines what configuration you are going to explore. So, when you are V to the power minus beta h, the temperature enters here and your energy levels are determined by volume and the interaction potential. There is a beautiful separation between the role of temperature and volume, which you also see in experiment and everywhere else. Now, how do I do the next one now? It is nothing but this bunch of Gaussian integrals and they are not interacting. So I have n integrals, right? So now I can remove all of them. Instead, I can do one integral and I remove this sum here. I have for n. Now we are on very familiar territory. Right? Alright. What is the value of the integral now? I just want to do one tiny little derivation to show you tell me what is the integral? Absolutely, because this is scalar. The vector set. So yeah, then it is how much? So it will be 3 of them. This is a vector. So dpx dpy, then again I can do that. X minus infinity plus infinity. Again I can break it. Dx, and I absorb it is 3n. Okay. Alright. Then as you said, 1 over n factorial e to the power n, then it becomes 2 pi m kbt to the power 3n. Okay. Actually, it should be h to the power 3n here, but I don't know what to do. But that comes denominator, but we are for the time being ignorant of the Planck's constant. So partition function of, we'll do this later also, j equal to a square n square, this part, this part. This is the ej here in particle in a box, right? And this is same problem as particle in a box. Since there is no interaction, what we are doing classical is the same what is quantum mechanics. And they give you huge amount of important information. From here we find a lot of important information we will do later. Now, we are, for the time being, we are not going to use it anymore, so let me remove this. So we have Qn 1 over n factorial e to the power n by n kbt Qn. Okay. 1 over 2 pi m kbt is right? Because it goes, so the equation is e to the power minus a x square minus infinity to infinity is root over pi by a, right? Right? That is the integration. Okay, so it's 3n by 2, right? Thank you. So 2 pi m kbt 3n by 2. Okay. Now, what partition function tells me that free energy is minus kbt ln q. Okay? All right. So, my free energy is this quantity, and as we claimed that this becomes an extensive property with n here and n here. Okay. Now let me do the following thing: P equal to minus dA dV T. Okay. So then I do from here, when I take log, do that, I get ln n kbt and I have a ln v here, right? Ln q becomes ln v, alright? N ln v. This is the only part I need because I am going to do derivative at volume at constant temperature. So ln qn brings an n, and I take derivative n ln v. When I take the derivative of ln v, I get 1 over v. So it is n kbt by v. Okay? So then you get PV equal to n kbt. So similarly, you get the entropy, and entropy is a very important equation, and that we will do later. And you can get specific heat from here. So is this clear? The PV you get out the ideal gas law, almost trivially, but not too trivially, but in a very systematic way. You now have a capsule for you that will gives you a partition. I give you an expression for partition function in terms of Hamiltonian and energy levels. You evaluate the partition function, then I tell you you have this exact relation, which is the most important relation of statistical mechanics, equation of statistical mechanics. In certain fashion, this one and the expression of Q, classical or quantum, these two together is essentially parallels what would be the Schrodinger equation in quantum mechanics. That means knowing these two, you know enormous amount of things. But you do need the energy levels. Now, in the case of classical system, when this quantity is Brn, dPn, e to the power minus beta h, you need the Hamiltonian. Okay, now people usually back and forth. In statistical mechanics, we do back and forth. In many systems, we don't need the quantum part, and so then very happily one can do like exactly this room temperature or similar temperature gas molecules in a box. We don't need quantum mechanics very much because quantum mechanics are not important. Then you do classical. But when you go to harmonic oscillator, what is the situation? Can you do it classically? Do you know this the famous theory of specific heat, Einstein? Okay, what is the specific heat of a gas? Ideal gas. Ideal gas. It is 3/2 R, right? 3/2 R. R is the gas constant. 3/2 NKBT, which will follow if I just go through this. The specific heat of ideal gas will follow by taking what is the A of specific heat? It will dsdt, right? d dsdt. And so I have the S from a partition function. I take the derivative and I get the dsdt. Now, there is a very important thing in the theory of solid state physics. That is the specific heat of solid. That is one of the core things that you study. So, where you taught the little bit of solid state physics and chemistry, what is Dulong-Petit's law? Why you don't know? How come you don't know? In PhD students and PSM students.
6.4.
Huh?
Product of specific.
Specific. So 6.4
Specific heat of solid.
Equal to 6.4 in data.
No, it is 3R. Specific heat of solid is 3R. That's called Dulong-Petit's law. That I taught even in high school. It's taught, right? Dulong-Petit's law. Okay. Now, at low temperature, the way this was a very beautiful story which was done by exactly this thing was done by Einstein in this specific theory, and then Debye corrected it. This is Debye Einstein Debye theory of specific heat. At low temperature, as you lower the temperature, the Dulong-Petit's law break down. And it is one of the early application of quantum mechanics to statistical mechanics, and again done by Einstein. So if I do the classical partition function here, I get 3/2 R, specific heat of solids. How do I get 3/2 R? One of the ways is the equipartition theorem, exactly correct. But there are the way that we do here, we can do by classically evaluating the partition function. Then I'll have a potential energy term. What will be potential energy term? Half kx square. If I put half kx square, I again have a Gaussian integral. You can do that integral. We'll do it later. And you get Dulong-Petit's law. So now, so what is now? Instead of in ideal gas, I get 3R. And here I get 3 by 2R. Okay, now the interesting thing happens when you go to low temperature, not too much low temperature. This Dulong-Petit's law breaks down completely. And which way it breaks down? Now think of the following thing. What is a specific heat? I told you in the very first class. The specific heat, the amount of heat you have to give to raise the temperature by 1 degree. Now you go to Dulong-Petit's law, well, it is 3 by 2R. Now you go to very low temperature. Very low temperature. You give temperature, their molecules are not heating. So there is a very important quantity that comes in, that is 0 point energy. Now you can give, you can increase the temperature of a solid by giving very little heat when it has almost no internal energy. So what does that mean? The amount of heat that you have to give is to go to, so what does it mean? Basically it goes to 0. So specific heat goes to 0, Dulong-Petit's law break down completely. And that thing was done. So the graph goes like that. With this I'll go. So this is Dulong-Petit's law, CV or Cp against temperature. This is Dulong-Petit's law, but real world it goes like this. And this derivation, this deviation from Dulong-Petit's law was derived by using classical partition function. In between. But the breakdown of the Dulong-Petit's law at low temperature was done by using harmonic oscillator thing in quantum mechanics, by using, it's in quantum, I cannot do anymore. I have to do this thing, quantum. And then Einstein evaluated that and he explained this result. Then divide found out there some extension 1 can do twice. Okay, this is it. Please go through the derivation few times because this is an important derivation.